1 minus j 1/2 tangent theta. Alright, after we do that, we're going to try to examine this term. We have a tangent 1/2 k l star. And the way we're going to analyze it is we're going to analyze cotangent. Ends up being easier this way if you look at it as a cotangent, and then you flip the results back over. So what does that equal? If you do some Taylor series expansion type of stuff, we end up getting this. Oh, and remember this was that number. So cotangent, we end up getting a cotangent, and this is right. And this is equal to, over here, instead of writing that, we can just write it like this, using this number. So that, with that in mind, if we break this up, we end up getting these two numbers. From this term, we get that, and from this term, we get this. So this is just how you break up the tangent term. If it has a small deviation, this is a small deviation from the tangent term, the real term. So we continue. So this is j. And if you look at the derivative, basically we're just adding the magnitude plus the derivative of a deviation. And this imaginary term we're assuming is the deviation. Now at resonance, omega is approximately equal to 1/2 pi. Okay? And at 1/2 pi, this becomes 0. And this becomes 1. And this is for the resonance. This is the resonance. Resonance, or you want to call it 1, or you want to call it n. At resonance, this is what happens. Therefore, the cotangent of omega star is going to be equal to negative pi over 4. Remember, this is this pi coming in here, and this 2 coming in there too, so that makes it pi over 4 tangent phi prime, or whatever. You don't have to do that. I don't know if I explained that, but okay. So let's go back to our original solution. We said that the displacement at 1/2 over L at the resonance frequency now is equal to d v L, which is also the thickness, multiplied by now this portion. This is the cotangent, 1 over k, okay? And then now we're going to put this cotangent portion in. And the magnitude, since we're finding the magnitude of the displacement, we're not caring about the phase. All of this talk I'm doing right is about the magnitude. The magnitude of the displacement is this. Instead of pi over 4, we're going to get this. So we have pi over 4, and at resonance, k equals pi over 2. Therefore, this number is going to end up becoming it's not pi over 2, it's just pi. 4 pi squared, and this is the 1 over tangent, so this is 1 over. So we have 1 over tangent. When you know the cotangent, you had to flip it over to get the tangent, and I just forgot to do that. So this is the actual term you have for the displacement. We're going to assume that the imaginary portion of this term, which we normally were including here, we're going to assume that that's not going to be not going to change the displacement much at all. So therefore, we just leave it out right now. This actually is a really good estimation of the displacement. Now I will continue, and we will talk about. Oh, great! So we solved the resonance frequency. Now we're going to talk about the total amplitude. So if you want to measure it, the entire displacement. I mentioned that it looks something like this at the first mode. This is the u displacement, this is the x coordinate position. The number which I calculated, this one right here, it is equal to this distance right here, or it is equal to this distance, which are the same. But if you want the total sort of displacement, you have to multiply this number by 2, which would make this 8. That's how you would find it. So sometimes, somewhere you might find that being mentioned as well. Right, so now we are going into understanding how do you find out this KEQ, the equivalent stiffness of the material of this form at this time. Well, you don't really need to do it now. You can use, you know the natural frequency, you know the mass equivalent, you know the force. So you don't really need to do the equivalent system model anymore. You already have this parameter equation, but we would benefit from doing it still. So the K equation, KEQ, how do you find it out? You analyze the resonance frequency. The resonance frequency squared is pi squared over L squared times 1 over rho S, which is a compliance. And that's going to be equal to the mass equivalent. The resonance frequency is the stiffness over the mass, right? Yeah, so the stiffness equivalent, so K equivalent over mass equivalent. This is going to be equal to rho L W T or H, whatever you like, and the stiffness equivalent, because we don't know it yet. So we can cancel things out. Okay, this cancels with this cancels with that. So basically, what we're left with, let's cross it out to make it more clear. What we're left with is that pi squared 1 L S W T, which is kind of like the cross-sectional area here. This is equal to the spring constant stiffness equivalent. And we see the only difference between this one, AC versus DC, meaning when we weren't applying a large field, you know, initially in the lectures before this, versus now what we're talking about, the AC resonance effect, where we have this, instead of having a DC strain looking like that, we have an DC displacement looking like that, we have an AC displacement looking like this, something like a sine versus a straight line. And this pi squared factor accounts for this type of weird shape, not weird shape, but it's a sine shape. And this pi factor accounts for that. So this is the spring constant that you're going to need to model a equivalent spring. Continuing the discussion, we calculated the displacement. Now, well, how do you get the displacement? You have the force. U at 1/2 L is the force equivalent. I'm sure you can see where this is going. Mass equivalent square root omega n squared minus omega squared plus omega n squared tangent, all this is under that square root, tangent phi, which is losses, squared. That's the magnitude. It's important to distinguish between them. And we want to know the phase, because the general solution at this point is going to be some magnitude multiplied by sine omega t, which is the forcing frequency, minus alpha. And we're going to say this alpha, this omega is not too far away from the resonance frequency. So we can say it's less than 1.5 of the resonance frequency, and we can say it's greater than 0.5 of the resonance frequency. In this range, approximately, this estimation of this model is good, because we're assuming that the mode shape or the effective stiffness of the material is equal to that effective stiffness at the resonance frequency. And this is how we're using it to deduce a 1 degree of freedom system model from a more complex model. Let's continue. So the phase in this case would just be the phase of a mass spring damper system model anyway, now that we figured it out. So for cases where the resonance frequency, and this is just to get the offset factor to work out. When the frequency is lower than the resonance frequency, we use this. You know, inverse tangents have their issues in the calculators, so this is one thing we use to help that out. But anyways, it equals. You're gonna see what I'm talking about in just 1 second. So it equals that. Above the resonance, below the resonance frequency, and above the resonance frequency we have pi plus tangent, and this is to get the offset because the coordinate system matching, and that's no inverse tangent. So minus. So this gives the phase. So now basically this completes our analysis of infinite degree of system freedom models to make it single degree of freedom. Mass spring damper, we just converted everything, and you can imagine now it'll be easier to use. This model will be easy to use when you want to describe other systems. You want to use other forces attached. Not only piezoelectric, you can add any type of force now you want. You can. This is simple. This is a system which is very well understood. You can use this, for example, in a control type model. You know, linear controls. Where oftentimes in elementary classes you learn about how do you control a mass spring damper system, but you don't learn how to control something weird like this. What is this? So basically, by linearizing it, the equations to something simple, you can use it for more complex analysis, if that makes any sense. So thank you for watching this video, which is in 2 parts. Next, I believe we'll go over some electrical analysis, which is very interesting. Thanks for watching. Thank you. See you next time.